Hi everyone, my name is Changmin Park and I'm a PhD candidate at the University of Buffalo. Today, I'm going to present our paper Rushmore. Rushmore is a system that securely displays static and animated images using TrustZone. Images are widely used on mobile devices, usually share private photos, doctors view medical images of patients, engineers share intellectual property. These images are confidential and need to be protected. However, are confidential images really protected? Here's a typical workflow to display a confidential image on a mobile device. First, trusted party sends a confidential image in an encrypted form, and an application on a mobile device decrypts the image and displays on the device screen. However, if the OS is compromised, the image on the screen gets revealed to adversaries. To solve this problem, previous approaches have shown that ARM TrustZone is a promising building block to use. Thus, I will give you a brief background on TrustZone. TrustZone is a hardware-enforced isolation technology built into ARM CPUs and widely used in commodity mobile devices. TrustZone provides two isolation domains called the normal world and the secure world. At any given point, a CPU core can only operate either in the normal world or in the secure world. In order to operate in a different world, a CPU core must make a world switch by invoking an instruction called SMC. The two worlds have their own applications and kernels, and the secure world is completely isolated from the normal world. This means that the normal world doesn't have access to the secure world, but the secure world has complete control over all hardware resources and can protect data or code execution. Thus, even when the normal world is compromised, the secure world can protect its code and data. Previous solutions have leveraged TrustZone to protect and display confidential images as follows. On a regular system, there is a display buffer called the frame buffer. Everything that's put in the frame buffer gets displayed on the screen. To display confidential images, previous solutions have used an approach where they create an additional frame buffer for the secure world. The exact details differ across different solutions, but the core idea is the same, and they create two separate buffers. A confidential image is put in the secure world frame buffer, and the image gets displayed on the device screen. Thus, it is protected. However, there is a critical limitation that the contents from the two buffers cannot be displayed simultaneously. A display reads from one frame buffer at a time. As a result, images in the known world frame buffer cannot be updated while the secure world is displaying a confidential image, such as updates on already displayed UIs after a user action, or images of received notifications. Rushmore is our solution that overcomes the limitation of previous solutions and does much more. Specifically, Rushmore provides the following three new capabilities compared to the existing solutions. The first is being capable of displaying from the known world and the secure world simultaneously. And the second is being capable of displaying animated images in real time at around 30 FPS or higher. The last is supporting visual cryptography as an alternative to regular cryptography. Before talking about Rushmore in more detail, I will show you a short demo of how Rushmore works. In this demo, I am using a quick mockup of a patient portal app. A doctor can use this app to examine a patient's fMRI scan, which is an animated image and needs to be protected. The app uses Rushmore to display fMRI images from the secure world, while everything else is displayed from the known world. This demo shows that Rushmore can successfully mix the visual outputs from the two worlds simultaneously. Such as the notification bar animation on the screen, the normal world shows updates on its UI displayed in the normal world, while displaying an fMRI scan from the secure world. Using previous approaches, this would not be possible. Then let's look at how Rushmore works to display confidential images. A main feature provided by Rushmore is secure display multiplexing. By default, there is the normal display channel, and Rushmore provides another display channel called the secure display channel. The normal display channel displays non-confidential images, and the secure display channels display confidential images. A confidential image comes from a trusted party in an encrypted form, After decryption, the image is displayed through the secure display channel. Rushmore provides a complete protection from decryption to final display on the screen. And images from these two channels can be simultaneously displayed as shown in the previous demo. To enable the secure display multiplexing and the simultaneous display, we use a well-known yet overlooked hardware feature called an IPU, Image Processing Unit. It is a media processor widely used in commodity devices for various functions such as noise reduction, sharpening, and rotating. An IPU provides multiple display channels that can be overlaid and displayed simultaneously on the same device screen. So Rushmore leverages two of the display channels, the main channel and the overlay channel, and use the IPU's ability to display the contents from all channels simultaneously. To protect confidential images, we secure the overlay channel using TrustZone. We assign the overlay channel to the secure world, which means that only the secure world has read-write access to the overlay channel. A non-confidential image is displayed on main channel in the normal world, and an encrypted confidential image is passed to the secure world, decrypted, and then displayed on overlay channel. Finally, images on two channels are overlaid together and displayed on the screen. At this point, even when the OS is compromised, the images on the overlay channel are still protected. In addition to displaying static confidential images, Rushmore can display animated images in real time at 30 FPS or higher. Let's look at how Rushmore is able to do that. 24 frames per second is the lowest frame rate that allows a human eye to naturally perceive motion. Rushmore aims for 30 FPS to provide a smoother viewing experience, and it should be able to display multiple animated images with various sizes. To provide faster frame rates, we need to minimize the end-to-end latency to display a frame from a confidential animation. However, there are two issues that need to be solved. The first is how to minimize the number of copy operations when sending an encrypted image from the known world to the secure world. The second is finding the right decryption methods, as decryption performance differs significantly across different crypto algorithms. In order to minimize the number of copy operations when sending an encrypted image from the known world to the secure world, we create shared buffers between the two worlds. Naive implementation requires two memory copy operations. The first operation is copying encrypted image data from the user space to the kernel space in the normal world. And the second operation is copying the data again from the normal world kernel space to the secure world kernel space. We have shared buffers that the normal world apps directly write and the secure world directly reads. And this minimizes the number of copy operations. In addition to minimizing the number of copy operations, we have observed that using the right crypto methods is an important factor in terms of performance. To find the right crypto methods, we have implemented and evaluated four algorithms. They are software AES, which runs entirely in software, hardware AES, which uses cryptography accelerator assurance module, Cha-Cha-20, which is a fast stream cipher widely used for mobile embedded devices as part of TLS and SSL, and visual cryptography, which is a specialized cryptography designed for image encryption and decryption. Out of these, the first three are standard crypto algorithms we evaluate. The last one requires more discussion as we adapt the design specifically for Rushmore to use it as a lightweight crypto option. Let's look at how the visual cryptography works in details. Suppose we have an original image, which is an image of the letter A. In order to encrypt this image, visual cryptography first generates a key image, which is an image with randomly distributed pixels. It then calculates pixel-wise XOR between the key image and the original image to generate an encrypted image. Now, only a user who has both the key image and the encrypted image can decrypt. To decrypt the original image, the only way is to overlay the key image and the encrypted image together. In the example decrypted image, it reveals the original image of the letter A. Then let's look at how Rushmore adapts the visual cryptography. Initially, a trusted server has an original image and a seed securely shared with a client device. On the client device, only the secure world has access to it. The trusted server generates a key image using a pseudo-random number generator with the same seed shared with the client device. Then the trusted server generates an encrypted image with the key image and the original image. Finally sends only the encrypted image to the client device. On the client device, the normal world displays the received encrypted image, and the secure world generates the same key image that the server used to encrypt the original image, by using the same pseudo-random number generator as the server and the shared seed. Once the key image is generated, the secure world displays the key image on the screen. Finally, the images from the two worlds are overlaid by the IPU and reveal the original image. Our implementation using parallel processing and a pre-calculated lookup table improves performance by 119 times over a naive sequential implementation. We use this for black and white images because we discovered that the decryption performance of visual cryptography for images that support 8 color is similar to that of ChaCha20, which supports 16-bit color images in our current implementation. Also, for developers who want to use Rushmore, we provide 3 types of support. First, the Rushmore client library for the normal world applications. Second, the Rushmore Android widget for the normal world Android apps such as a button, an image holder, and an animation holder. And third, the Rushmore service interface for the secure world services that can customize how to display confidential images. Finally, to evaluate the capabilities of Rushmore we have seen in the previous slides, we answer questions in 2 categories: performance and security. For performance, we answer the following questions. What is the latency when Rushmore displays static images? What frame rates Rushmore achieve with different crypto methods? How does Rushmore affect performance of the workload running in the normal world? And how do the shared buffers impact performance? For security, we answer the following questions. What is the size of TCP for Rushmore? And how does Rushmore defend against potential attacks? For the performance questions, due to the limited time, we will just show a short video that demonstrates the performance of Rushmore. And for the security questions, we will just show the TCP size due to the limited time once again. All other questions are answered in the paper. For performance questions, we show a short video to give a sense of how Rushmore performs in general. In this demo video, the secure world displays an animation while the normal world runs a benchmark app. The benchmark app we use is Passmark, and it contains 26 benchmarks in 5 categories: CPU, memory, disk, 2D graphics, and 3D graphics. We can see the single cube animation being displayed in the middle of the screen using the secure overlay channel, while Passmark is using the main channel to display its own content. The single cube animation is being displayed in 30 frames per second, and even when running with 2D and 3D graphics benchmarks. Rushmore successfully displays the single cube animation without a lag. Details with benchmark app's core results are in the paper. For security questions, we show the TCP size of Rushmore. Rushmore is built using Opti, which is an open-source trusted execution environment for TrustZone, and we count only the components that we added or modified. The table shows the lines of code of each component we added. The size of other components are stable, but the size of cryptography module changes depending on which crypto method we enable. If we enable ChaCha20, a size of crypto module is 0.3K, and a total size is 1.5K. And if we enable visual cryptography, then the size of the cryptography module is 0.9K, which is a little larger than ChaCha20, because of an extra implementation for a pre-calculated lookup table that improves performance. So total size is 2.1K. Although we cannot do apples-to-apples comparison, our TCP size is comparable to previous systems that have used Opti for their implementation. For example, V-button reports additional 1.3K, Trust Token app reports additional 4.5K, and Trust View reports additional 3.4K. In conclusion, Rushmore is able to display from the known world and the secure world simultaneously by leveraging IPU's multiple display channels, and provides real-time frame rates 30 FPS or higher by minimizing the number of copy operations when sending an encrypted image from the known world to the secure world. And using the right decryption methods as decryption performance differs significantly. Rushmore also supports visual cryptography as an alternative to regular cryptography, and it is the best crypto option for black and white images and lightweight. Our code is available at the URL below. Thanks for listening.